Welcome to Math 150, Section 2, 2021, Lecture 29. This is the last of the review sessions. There are a tremendous number of review lectures posted online. This is one of the advantages of being able to record things. I am happy to do the same problems we did in the first section. I'm happy to do different ones. So you know what was done is we did level sets. After level sets, we did example of interchanging order of integration. We then talked about convergence of Taylor series and just talking about how do you use things like the root test. And so I believe those were the topics that were covered. So again, happy to do all that stuff again. If there are any specific questions you have, I would prefer to start with those first, just to maximize the amount of different material that is covered.
Maybe like an example of, I don't know if this would be on like when you have a series, finding like a general bound of where it might converge to.
Sure. And so let's say I give you the following sum. The sum n goes from 0 to infinity of an say x to the n. And so this could be Taylor series. And so maybe an is the nth derivative at 0 divided by n factorial. And if that's the case, I want to know when things converge. Now we know that n factorial is approximately n to the n e to the minus n squared root of 2 pi n. So n factorial to the 1 over n is approximately n over e. And this is because if I just take the 1 over n power, do it this way. When I take the 1 over n power, n to the n to the 1 over n is just n, e to the negative n to the 1 over n is just e to the negative 1, and we know n to the 1 over n converges to 1. And similarly, the square root of 2 pi to the 1 over n converges to 1. So after you do a little bit of algebra, you see that the nth root of n factorial is about n over e. So if we want to try to understand something like this, what really matters is the size of the nth derivative at the origin. That's going to be what controls how large of a region we have with the series convergence. Okay, so let's write out a little bit more explicitly. Let's say it's the sum n goes from 0 to infinity, the nth derivative at 0 over n factorial x to the n. So we have lots of different tests we could use to try to find out whether or not this converges. N factorial is growing tremendously fast. X to the n is only growing polynomially fast. And so because of that, we expect that this is going to have good convergence properties, so long as f of n is not growing too rapidly in the nth derivative at the origin. So for example, imagine the nth derivative of the origin is always less equal to some bound b. We have to be a little bit careful if we wanted to use something like the ratio test, because if any of these derivatives happen to vanish or become really, really small, when we divide, that could actually give us something that's larger and the limit might not exist. So the ratio test is not necessarily a good test to use for this. What might be a good test to use? So not the ratio test, what should we try? The root test. I mean, we don't have that many. We have comparison, ratio, root. This is almost surely not going to be an integral test. Okay, so let's look at rho equals the limit as n goes to infinity of the nth derivative at 0 to 1 over n, x to the n to the 1 over n, divided by n factorial to 1 over n. This is the limit as n goes to infinity. Well, we'll have b to the 1 over n, and x to the n is just x, and then n factorial to the 1 over n is about n over e. What is this going to go to? As n gets very, very large, what does b to the 1 over n go to? It goes to 1. So the numerator is bounded. The denominator goes to infinity. So what does this whole thing go to? It goes to 0. So it converges for all x. So if we're in a situation where the nth derivative is bounded, the Taylor series converges for all x. Can you give me an example of a function whose derivatives are all bounded? Well, you have to give me an explicit function. You know at least 2 of them by name. So what are the standard functions? Okay, so there's the polynomials. What else? And again, any finite polynomial will work, but it's not interesting because the Taylor series will just be a finite polynomial. Okay, what other functions do you have? Logarithms? What else? Trigonometric. So of the logs or the trigs, can you think of any of them that has a bounded derivative? And derivative of derivative, and derivative of derivative. Yeah, the derivatives of sines and cosines, they just keep flipping back and forth. So if I give you sines and cosines, all the derivatives of sines and cosines are going to be at most 1 in absolute value. So this tells us that the Taylor series of a sine and a cosine will converge for any value of x. Okay, so now let's imagine that instead of having the nth derivative, let's say go to b, let's say the nth derivative was really large. Let's say it's approximately n to the n. Well, n factorial is like n to the n e to the minus n, so this is much, much larger than n to the n. Let's see what that would do. And the nice thing about being a blackboard is I can just erase that small little bit over here. And now this would become n to the n to the 1 over n. That's just n. This becomes x. This is n over e. So this is just ex. So when does this converge? So what values of x would this converge? We're using what test? We're using the root test, right? Rho is equal to ex. So when does this converge? Yeah, so it converges if the absolute value of x is less than 1 over e. So even if we're in a situation where the nth derivative is going really fast, n to the n, it's going faster than n factorial, we still have a decent radius of convergence. Let's do one more tweak. Instead of saying it's growing as fast as n to the n, let's have it go a little bit slower than n to the n. Let's say it's about size n, 3n over 4. And so if we do 3n over 4, it's large, but it's not going to be as large as n factorial. Okay? And so now when we come over here, it'll be n to the 3n over 4 to the 1 over n, it'll be n to the 3/4. Because I'm just replacing now the nth derivative of 0 with n to the 3n over 4. I take the 1 over n's power of that, and that will just be n to the 3/4. Well, we have n to the 3/4, we have an n down here. This is the same as the limit as n tends to infinity of ex divided by n to the 1/4. What does that limit equal? It's 0. So where does this converge? Sorry? For all x. So there's a really good chance that your Taylor series could converge for all values of x. If you have some reasonable decay rates. Now imagine I give you f of x is e to the x squared. And I want to find the Taylor series for this function. And I want to find where does it converge. I could start taking derivatives. So f prime of x would be 2x e to the x squared. Right? What would f double prime of x be? I'm sorry? You have to do the product rule, then the chain rule. So first when we do the product rule, it would be the derivative of 2x times e to the x squared would be 2 e to the x squared. And then we would have another 2x coming down, so it would be 4x squared. And you can start to see it's going to become a nightmare. If I then do the third derivative, if I'm doing this correctly, it would be 4x e to the x squared. And I'm going to take note of this part, would become 8x e to the x squared plus 8x cubed e to the x squared, and so on and so on. Yes. And so if I try to do it like this, it's going to become extremely painful. What you just noticed is, well, we know the Taylor series of e to the u is just the sum, n goes from 0 to infinity, of u to the n of n factorial, let u equal x squared. Oh, okay. So the Taylor series of e to the x squared is then just the sum, n goes from 0 to infinity, of x to the 2n of n factorial. And if you look at the painful algebra that we were doing, you can see the odd derivatives are always going to be 0 at x equals 0. And the even ones are going to have a term that doesn't involve any x's. And when I take the next derivative of this, when I use the product rule of the 4x e to the x squared, when the derivative takes the 4x and we get 4 e to the x squared, that's not going to be 0. And so there's lots of ways to see this. This Taylor series is going to be very similar to what we had before. And it will similarly converge for all values. So when you have something like a Taylor series, the root test is probably the best one to use, because if you ever have one of the derivatives vanish, if you try to do a ratio, you then have that in the denominator, and that gives you a infinity, and then the limit doesn't exist. And remember, if we're doing the ratio and the root test, it's only when the limit exists. If it's less than 1, it converges. If it's greater than 1, it diverges. If it's 1, there's no information.
So would there ever be like a scenario where it converges and like the sum is something other than 0 and you were supposed to find what the sum would be?
You mean if I give you a sum and ask you to approximate the sum? Yeah, I can absolutely ask you to approximate the sum. And there's only 2 ways you can really approximate the sum. The first is if you know what it converges to. And then the second is we have one test that does give us an approximate value. It's the integral test.
I'm a little confused, I guess, like, because I know you're supposed to add up something to the beginning.
Right.
I'm not sure what it is.
So let's just do the integral test again. And then what's nice is this is something that's different in section 1. And we've known each other a semester. It's boring doing the same examples twice. In the fall, some professors have to do it 3 times in a row. And it's an interesting question. Would you rather have 2 different classes to teach, which is a lot more work and a lot more prep, or the same class twice, which is much more efficient as a professor, but you have to then do the same thing multiple times? So I'm actually much happier when I get to do a slightly different example and say, well, if we don't get to integrating by switching the order, just quickly put it on the 1.5 speed. All right, so let's do the integral test. So we'll assume the sequence AN is non-increasing. There is there's a similar analysis that would go on if it non-decreasing. Let's do the special case, an is 1 over n. Here's 0, here's 1, here's 2, here's 3, here's n minus 1, here's n plus 1. So if I want to try to estimate what is the sum of an, maybe I want to look at the sum k equals 1 to n, and I want to estimate it. Well, all of these rectangles have thickness 1. So if I have the height be ak, then each rectangle is going to be that corresponding term. So the first term, I go up to a height of 1. The second term, I go up to a height of 1/2. The third term, I go up to a height of 1/3. And the nth term, not going to steal, is a height 1 over n. And if I add up the area under all these rectangles, that's the area of my sum. So if I draw the function y equals 1 over x, notice that that function is always strictly less than my boxes. And so what I would have, and this is where it's annoying that you have to be a little bit careful. If I integrate from 1 n plus 1 of 1 over x dx, that's less equal to the sum, and it goes from 1 to, k goes from 1 to n of 1 over k. And I have to be a little bit careful that because I'm starting here and going to the right, the integration has to go all the way to n plus 1. Now, instead of moving everything to the right, I could, of course, move everything to the left. And if I move everything to the left, I would have my boxes going like this. And so if I do my boxes like that, now all of a sudden, my function is now larger than the box, except I missed the first box. So now, I would get that this is thus equal to a1, the first box, plus the integral from 1 to n of 1 over x dx. Right? So we've almost approximated the sum with the same integral. So I can write this as the integral from n to n plus 1 of 1 over x dx plus the integral from 1 to n of 1 over x dx less equal to the sum k goes from 1 to n of 1 over k is less equal to a1 plus the integral from 1 to n of 1 over x dx. Now, I can actually evaluate this integral, it's not too bad. But the other thing is, if I just want a lower bound for this, I can just use, sorry?
I was wondering why
Sorry?
what is the bottom one
This?
Yeah.
Well, because I'm integrating from 1 to n plus 1.
Oh.
So I write it as 1 to n and
Right,
n to n
okay.
plus 1. And so what I'm doing now is I'm just trying to get a decent bound without too much work. It's actually beautiful how great formulas you can get from stuff like this. If I look at this, I'm integrating from n to n plus 1. Well, my function is decreasing, or it's at least not increasing. So on this interval, I know f of x is greater than or equal to an plus 1. So we know an plus 1 plus the integral from 1 to n of 1 over x dx is less than equal to my sum, integral from 1 to n of 1 over k, is less than equal to a1 plus the integral from 1 to n of 1 over x. Okay, so that's not so bad. Now we have the same integral above and below the sum. And we know that this sum is at most the integral plus a1, and it's at least the integral plus an plus 1. So now we have a really good estimation in terms of how much can we be off by. So how much is the lower bound different from the upper bound? So upper minus lower is what? A1 minus an plus 1. And if the series is non-increasing, this is actually just less equal to a1. So we know that the sum is within a1 of the integral from 1 to n of 1 over x dx, which is just the natural log of x. So we're evaluating that sum to within 1. That is a pretty good evaluation. Now you have to always ask yourself, when is this worthwhile? Instead of taking the function 1 over n, I'm going to do a search and replace and do 1 over n squared. All right, so this is still 1. This is now 1 over 2 squared, 1 over 3 squared, 1 over n squared. And so we now know, doing the same argument, that the sum, and now I'll go, n goes from 1 to infinity of 1 over n squared, because it converges, I can let it go all the way up to infinity. Is within a1, which is 1, of the integral from 1 to infinity of 1 over x squared dx. What is the integral of 1 over x squared dx from 1 to infinity? Cannot be -1. Right, because it's a minus, we have to flip the order integrated. Why did you, and we know it can't be -1 because it's 1. Right, so this is equal to 1. So it tells us that the sum of 1 over n squared is within 1 of 1. It's true, this is pi squared over 6. Is it a big deal to be within 1 of pi squared over 6? Is this a good accomplishment? Should we be proud? Yeah. I'm not that excited about being within 1 of pi squared over 6. So you always want to get a sense of how good is the result. How do you want to measure being off by 1? So I apologize to constantly using Bill Gates, but Bill Gates and Melinda Gates, I think the marriage is not going well. Are they going through divorce proceedings? So what is going to be extremely important to know going through divorce proceedings? Who gets what? So they need to know the assets. Imagine I tell you we can evaluate the assets of the Gates to within $1. That's pretty good. Okay. Normal human beings, let's say we can evaluate you to within $500,000. For a lot of people, that's a huge error, being off by $500,000. What about Bill and Melinda Gates? If you're within $500,000, is that essentially no error? Yes. The scale of money we're talking about, $500,000 means nothing. Look at the logarithm up here. Look at this, the harmonic series. That's going off to infinity. It's getting arbitrarily large. So to be off by at most 1 to a function that's going off to infinity, you basically nailed it. But a function that's of size 1 to begin with, pi squared over 6, it's more than 1, it's less than 2. To be within 1, that's not that impressive. You want to look at the percent error. And the percent error of being off by 1 is, this is you would imagine it being off by 50%. It's not a great bound. How could we do better? So we agreed that we should not be celebrating the fact that we are within 1 unit of the sum of 1 over n squared. But I claim with just a little bit of work, you can do better. Now, the other thing is, to some extent, when I tell you that we're going to approximate 1 over n squared with 1, do you think that is a good bound? Do you think it's a little bit too small, a little bit too large? So you think that approximating the sum of 1 over n squared with 1, that 1 is too large, that the actual value is less than 1? Well, think about what is the sum of 1 over n squared? So you want to sum n goes from 1 to infinity of 1 over n squared. What does that equal? Okay, but give it to me in a recipe that I can actually try to do on a calculator. It equals. Okay, plus what? Plus what? 1/9. So when I tell you I'm going to say that the sum is 1, this is a no shit.
Yeah.
Right? If I look at just the first term in the sum, I've already got 1. So basically, you do all this work of the integral test, and you say, we're going to approximate the sum with 1. And we're going to, now, is that bad? Yes. But the integral test does a little bit better than saying we're going to approximate it by 1. We're going to approximate it by 1, and the error is at most 1. Okay, that's useful. It's telling us that from 1/4 onward, the error is at most, that sums up to at most 1. What we could do is, let's just collect the first couple of terms. Add those just by brute force, and then apply it going forward. And so now let's look at from 1 over 4 squared and on. So I will open up Mathematica and just calculate a few things. Okay. So pi squared divided by 6 is approximately 1 point, my computer's just extremely slow right now. Approximately 1.644. This is approximately 1.644. Right? We do 1 plus 1/9. It's 1.36. And now, if we add from 1/4 onward, this is about the integral from 4 to infinity of 1 over x squared dx with an error of A4, which is 1/16. What is the integral of 1 over x squared? What function is derivative of 1 over x squared? Negative 1 over x. And then we flip the order of integration, so we get 1/4. So it's about 1/4 plus the error at most 1/16. So we would have the 1 plus 1/4 plus 1/9 plus 1/4. So that's 1 plus 1/4 plus 1/9 plus 1/4 is approximately 1.61. And 1/16 is about 0.0625. All right, so now we're saying that the sum is about 1.611. The actual value is 1.644. And we're saying that the error is at most 0.0625. So by just taking a few terms in the beginning and then applying the integral test from that point onward, we actually got a pretty good answer. So what if you wanted to do a little bit better? What would you do instead? You do a few more terms. And the terms are getting smaller and smaller and smaller. And you can say, hey, wait a minute, my error is basically the first term I don't keep. So if I go all the way and do the first 10 terms, my error is going to be 1/10 squared. That's going to be of size 0.01. So if I sum 1/10 squared, and it goes from 1 to 9, I get 1.53. Then I have to add in a 1/10 from that. So add in 0.1. And so I get 1.639 versus 1.644. Well, 1.639 does round to 1.644. So I've gotten the first two decimal digits correct after taking just 10 terms. And so this is a really good general principle. And this is the last lecture I had, so it's not a bad opportunity to try to highlight something like that. Just because something isn't great to begin with doesn't mean you can't tweak it a little bit and set it up into a situation where it can succeed. And so trying to use that for everything was just terrible. But if you do a few terms by hand first. Okay. So this is the integral test. Absolutely wonderful test. And it's the only test that we have that actually gives you a way to estimate the value of the sum of two. And for a lot of things, we don't need an exact value. We just need something that's approximate. And it's great if you can know what the error is. One of the favorite classes I have to teach is operations research. My students have done a lot of work with local businesses. And frequently, it is too hard to find the optimal answer. But you have wonderful theorems in mathematics that can actually prove that you're within a certain percent of the optimal. So even though you don't know what the optimal is, you can actually prove that you're off by no much more than a certain amount, which is wonderful. Okay. Anything else to discuss? So again, it's good that we're doing slightly different things in section 1, and what you can do is you can just watch the section 1, and if you say, oh, okay, I'm comfortable with integrating by parts, or I'm comfortable about exchanging modes of integration, or I'm comfortable with finding volumes between regions, I can skip those sections, and if not, you can just watch those sections. Sure. So I'm going to deliberately choose maybe a bad maximum so that we know what the answer is ahead of time. So consider g of xy is 4x squared plus 9y squared equals 1. And I want to maximize the function f of xy equals x squared. What kind of curve is 4x squared plus 9y squared? It's an ellipse. Now I can write this as x over 3 squared plus y over 2 squared. Equals 1. I divide both sides by 36. I divide by 36. Oh, no, I've got it equals to 1, never mind. Okay. I've already set up for the one side. I can write this as x over 1/2 and y over 1/3. So I can write 4 as 1 over 1. So I can write it like this and just make it, clear that this is an ellipse. Okay, so when you look at your function, where do you think the function x squared is going to be largest on this ellipse? So when you look at this ellipse, where do you think it's going to be largest? So x goes from -1/2 to 1/2. Y goes from -1/3 to 1/3. You have the function x squared. If I have to stay on this ellipse, which value of x is going to give us the function f of x, y equals x squared is largest? Which point x, y is going to give us this function's largest? Yeah, or, so this is one of the points, a -1. So I've deliberately chosen this function because I can clearly tell where it's going to be largest. It's going to be largest at plus or minus 1/2. And then after we do this, we'll then adjust it a little bit and make it a little bit more interesting. So I have the gradient of f is df dx, df to y, that's going to be 2x comma 0. The gradient of g is dg dx, dg dy, and that's going to be 8x 18y. So we want to solve, grad f equals lambda grad g, and g of xy equals 1. All right, so what does that mean? It means 2x equals lambda 8x, 0 equals lambda 18y, and 4x squared plus 9y squared equals 1. So when you look at these three equations, one of the equations should jump out to you in terms of it gives you useful information. The second one, either lambda is 0 or y is 0, or both. Well, if lambda is 0, then x is 0 and it's not on here. So case 1, lambda equals 0, no solution. So case 2, lambda does not equal 0, therefore y equals 0. So if y equals 0, lambda is just going to be 1/4, right? Because the x can't be 0, because if x is 0, there's no solution. But we don't really care what lambda is. We know that once y equals 0, 4x squared equals 1. So 4x squared equals 1. So x equals plus minus 1. And those are our candidates. So we were able to solve this pretty easily by doing the algebra. But we could also have done this by doing the Lagrange multipliers. And when we do the Lagrange multipliers, it's not a big deal. Okay. What if I gave you x squared plus 2y squared? So we're going to change things now. Where would you rather be? Well, if I take the point 1/2, I would get 1/4. If I take the point 1/3, I would get 2/9. Which would you rather have, 1/4 or 2/9? I'd rather have 1/4 because 1/4 doubles to 2/8. 2/8 is better than 2/9. So I know that 1/2 is better than 1/3, but maybe there's an intermediate point that's better. So it's no longer immediately clear where my best point is if I have x squared plus 2y squared. And so what changes? Well, this is the nice thing about being at the blackboard. The 0 becomes what? So I need df dy is 4y. The dg dy hasn't changed, so I come over here now. Now I get 4y equals 18y. Okay, so when I look at this, I know that lambda can't be 0 because if lambda is 0, there's still no solution. So let's assume lambda is not 0. So now things become a little bit more involved. And so rather than trying to squeeze this into one board, let's just do this carefully. So case 2, lambda does not equal 0. So the 2x equals lambda 8x, that's the same as x equals lambda times 4x. And the 4y equals lambda 18y is the same as y equals lambda divided by 4, 18/4 is 9 pounds. And now I have 4x squared plus 9y squared equals 1. What do you think the solutions are going to be? Is it possible that both x and y are 0? So we could do, let's imagine what happens if x is 0, if y is 0, and then if both are not 0. So sub case 1, y equals 0. Sub case 2, x equals 0. Sub case 3, x and y are both not 0. Well, if y equals 0, what do we know? Well, if y equals 0, x can't be 0, or there's no solution. So then we get 4x squared equals 1. So x is plus minus 9. If x equals 0, y can't be 0, or it's not going to solve g. So then we would get 9y squared equals 1. You get y equals plus minus 2. And if x and y are both not 0, well, if x and y are both not 0, if x equals lambda times 4x, what do we know about lambda? Lambda is 1/4. But when we look at the second equation, what do we know about lambda? Is 0 to 2/9. So no solution. So again, see how we broke it up into lots of cases. We first did case 1, lambda is 0, and we dispatched that. And for the second one, we had some algebra to do. We had a lot of cases here. And much rather do a lot of easy problems than one hard problem. And so by doing a lot of easy problems, you have more subcases to consider. Okay, I would rather just carefully keep track and just make sure that I haven't forgotten anything than to try to do it all at once. And by breaking it up into lots of different cases, well, if y equals 0, then I know it's 4x squared equals 1. If x equals 0, then I know it's 9y squared equals 1. And if x and y are both not 0, I can cancel the x, I can cancel the y's, and now I get aha. Or if x and y and lambda are not 0, we could take ratios, right? And if I take the ratio, if I divide the first equation by the second, I would get x over y, the lambdas cancel, I would get 4 divided by 9 halves x over y, or x over y equals 8/9 x over y. No solution. So what this is basically telling me is that when it's just x squared, you want to just have all this, you want to just be at the point plus or minus a half. Even if you go up to x squared plus 2y squared, it's still not worth moving away from the x squared. You lose too much as you move away from it. But at some point, the coefficient in front of the 2y squared is going to be enough that you no longer want to be an x squared. Right? Imagine I gave you 1 billion y squared. Okay, clearly if I give you 1 billion y squared, you will now want to be at the point 1/3 or -1/3. So the question is, do you move continuously from the plus or minus 1/2 to the plus or minus 1/3 as we change the coefficient of the 2y squared? It starts off with x squared for a while, and then maybe it slowly moves until we get to the plus or minus third. Or maybe it stays here, and then all of a sudden there's this critical value where all of a sudden you're indifferent between the two. But both of them give you the same value, you're indifferent. And then if you go over just a bit more, you're no longer indifferent, you want to get plus or minus a third for y. So those are the two possibilities that could happen. And it's not clear looking at this if you're going to have a continuous movement, or if you're going to just have all of a sudden, you'll have one moment of being indifferent. And then after that, you will then help. So if you want this extra credit, you try to figure out, does it move continuously, or does it just hop from one to the other? All right, so this is a good place to start. Pause the recording.